All right, so probability. So I have to admit, you know, of all the subsets of mathematical study, probability is the one I tended to like the least when I was in college, because it just had a, I don't know, like a kind of an absurd uncertainty. You know, problems were almost interpretive at the highest level in probability, and you could make a strong argument for multiple things being true. I just didn't like that. It's not what appeals to me mathematically. I like one certain absolute answer with no doubt involved. And probability sometimes doesn't work that way, but I'm going to focus on the aspect of probability that does. So the main idea in probability, the thing that you really can't get away from, is this formula for the probability of an event occurring. It is the number of ways something can succeed over the total number of outcomes. And if you think about the simplest example, flipping a coin, let's say I call heads, I flip and catch it. How many ways can it land on heads? How many head faces does the coin have? One. How many total faces does the coin have? So that would be 1 out of 2, or 1/2, 50%, exactly what you'd expect. It can be written as a percent, 50%, a decimal, 0.5, or a fraction, 1/2. In every case, the answer can only be between 0 and 1. So this is sort of the essential idea of probability. That successes over total outcomes. And many of those really complex and crazy formulas you're going to see if you take calculus-based probs and stats like I did in college are derived from this very simple formula. So successes over total outcomes, written as a percent, decimal, or fraction, and it can only be between 0 and 1. Let me know if you guys have any questions, thoughts, or comments. Okay, so sample space is some terminology we need to familiarize ourselves with. It's all the possible outcomes of an experiment. So an example, if I'm choosing a card from a deck, and let's say I've removed the jokers. There are 52 cards in a deck, so the sample space is all of those 52 possible cards. Cards are such a great example in probability, but I run into a problem recently. Kids don't know the suits and the cards. They just don't know. Like, you know, what are the 4 suits?
Club, spades, heart, diamonds.
Very good. What are the face cards?
King, queen, jack.
Okay, so Kobe's a counterexample. But a lot of young people just simply don't know that nowadays. And it's surprising. Didn't grow up playing cards like my generation did. At least not in analog form. Maybe you played solitaire on a computer or something. An event is a single result of an experiment. So if I toss a coin, that's an event. If I roll a 5 on a die, that's an event. If I have a spinner on a board game and I spin and it lands on blue, then that's an event. If I don't know, try a field goal in a football game, that's an event. There's a probability of being good that is not 100%.
Are you sure people don't know the suits?
Yeah, it surprised me, Colby, but for the last 2 or 3 years when I taught this section and had a little homework lesson or whatever, kids' hands would go up. What does it mean 13 in each suit? You know, or I'd get a question like, how many kings are in the deck? So.
Have they ever played Go Fish?
Apparently not. A lot of young people just simply don't. I think they sit in their rooms and play their PlayStations and never come outside.
Yeah,
Not for even to come down to a family dinner.
go fish is a classic.
Agreed. I grew up playing a lot of those things. Okay, so remember that all probabilities fall between 0 and 1. 0 is an impossibility. So if I were to, analyze my chances of jumping to the moon, I would come with 0. 1 in 6 chance is an example of an unlikely event. Getting heads or tails on a coin flip is an example of something that has an even chance. Saying that I have picking from these balls and picking a blue one, that's something that's likely. And then something that is certain. Well, it's hard to find absolute certainties empirically. The universe eschews certainty, but certain things are effectively certain, like the sun will come up tomorrow, or you will go to your second period class at 9:15. Those are effectively certain. They're not absolutely certain, because our universe does not like certainties. Okay, any questions about anything so far? All right. So when something is probable, it is likely. When something could never happen, effectively, it is impossible. When something is not probable, it's unlikely. And when something is surely going to happen, it's certain. So you guys, you don't need to write that down again. Just familiarize yourself with that terminology. Okay, so this is a virtual coin flip. Anybody care to bet on this? Gracie, what do you think? She calls head. Let's see. And you lose. So we'll just do a few here. Tails again. Heads. Tails. Tails. Gosh. So that's where we're at currently. All right, that's a pretty big one. I suppose I should use the tally mark convention. Interesting side note, you know the how they do tally marks in Asia? I consider it superior. It's like this: 1, 2, 3, 4, 5. So if you go to a restaurant and you order something, like you order 4 egg rolls, they'll write the Chinese character for egg roll and that. And if you order 3, whatever, that'd be that. It's pretty interesting. As usual, their mathematics is concise and effective. Now, we did an empirical experiment. We didn't get 50%. Why? Why didn't we get exactly 50% heads versus tails? Well, because our sample size is too small. We did 8 trials. If we had done 1,000 trials, it would have been closer to 50%. If we'd done 10,000 trials, closer still, and so forth and so on. So the more trials you have, the more it will revert to the mean or exactly what the probability is. If your sample size is small, you can deviate from the expected probability greatly. If your sample size is large, it's less and less likely that that would occur. So small sample sizes can deviate from your expectation. So what's the spinner going to stop on? Orange. But if I spin it again, what's the probability that it will land on this color? What do you think, Kobe?
1/4.
Good. What about this color, Gracie?
1/4.
Good. Raleigh, what about orange or red?
1/2.
Good. Now remember Roy G. Biv. So all these are rainbow colors. What's the probability that it lands on a color of the rainbow? 1. So I guess technically it could land on the black line between them, couldn't it? That's where you get into weird. You could always overanalyze a probabilistic argument and make it ridiculously complex if you wanted to.
There's a probability that the arrow goes off the spinner.
Or that the computer crashes, or the power goes out in the building, or a meteorite strikes Elizabethton High School. You know, again, if we want to really analyze this, we could go all the way down the rabbit hole to the end of time.
Probably 1,364,000.
Indeed, yeah. Okay, so here's a die. I like how it talks. This is really fun.
6.
6. Almost sounds British, doesn't it? With the over-enunciation of the consonants.
It sounds Chinese.
6. One of the key elements of a British accent is to over-enunciate your consonants. At least the erudite British accent. If you want to do a Cockney or something like that, which is their urban accent, it's kind of like the analog to a New York accent in America. So urban Londonites, for example, would speak with a Cockney accent. And if you ever watch those movies like Lock, Stock, and Two Smoking Barrels or Snatch with Brad Pitt, if you guys haven't seen that, man, you should watch it. It's hilarious. Not kid-friendly, but hilarious. Okay, what's the probability that we'll roll a 2 here, Mason?
1/6.
Good. What about a 5, Colby?
1/6.
What about an even number, Riley?
1/2.
Good. What about a number less than 10, Gracie?
30.
Indeed, 1. So you guys have the idea, I believe. All right. Any questions about any of this so far? Just straightforward probability. But again, if we went down the rabbit hole, we could make these problems extremely complex. We have to simplify them so that we could understand them. Oh, we don't need that, I don't think. So this is a problem I want to set up for you. So it's a classic problem in probability. It's called the Monty Hall problem. So we're making up a game show. Monty Hall was a game show host back in the 60s and 70s. And we're imagining he has a game show where a contestant is presented with 3 doors. With me so far? So you walk out, you got 3 doors. You're going to choose one of the 3. Now, behind 2 doors is a goat. That's kind of the shtick of the game. In other words, what makes the television audience interested. And behind the other door is some great cash prize. $1 million, let's just say. So you could win a goat, or $1 million. Nobody knows which door is which. So I pick a door. And then there will always be at least 1 goat remaining, do you see? So the host will know which door has the goat remaining and will open that door, reveal the goat to the audience, and then offer you the opportunity to switch doors. Do you do it or not? And there is a right answer. So what do you think? $1 million on the line. Do you swap or not?
I think this is, you get to keep the goat.
Yes.
Well, it's the 70s. You can probably get away with making a lot of money off the goat.
Well, a few thousand. It's not quite $1 million, certainly. So the $1 million is an objectively better prize.
Oh, it depends. It's on a goat farm.
Well, we'll assume that it is for the purpose of this problem. So do you swap or not? Again, there is an absolutely right answer.
Why not?
It-
Stay with your answer.
It is, and like I said, it's a classic problem because it confounds people exactly as it's confounding you now. It seems like both probabilities would be what? 33%, right? But it's not quite the case because the original door that you chose, let's say I chose 1. Then the game show host opened 2 to reveal the goat to the audience, and then invited me to trade my door for door number 3. Do you see how when I first chose this door, we'll imagine no goats are known. This is a 33% chance to be the million. Everybody agree? But the 2 remaining doors, what is the probability? Well, 66.67, so we'll just say 67% for simplicity. Do you see how when the game show host opened this door, that remaining probability was absorbed by door 3? So door 3 now has a 67% chance to be the right door. In other words, you should always swap. Now, does that mean you will always win if you swap? No. But it is statistically advantageous to do so. So you should always swap in this scenario.
But can't that be used against you?
How so?
Because if you know that, if the game show knows that, couldn't they just make it in the door that you choose?
Well, considering if the game is rigged, yes. And a lot of game show games are rigged. We're imagining this one is not. In fact, I think there was a famous game show, the $64,000 question or something like that. That was in the 50s that they proved. Somebody went back and did a statistical analysis and somehow proved it was rigged.
I think they're all rigged, except the ones you physically can't, like Jeopardy.
Yeah, that would be hard to rig. I think probably more of them are than are not. It just makes sense. Producers would want to control. Did you guys ever hear about Press Your Luck guy? Gary, I want to say Gary Lansing was the name of the guy, but might be wrong about that. So there was this guy that was a super fan of the game show Press Your Luck, which you may have seen on some old clip. It's people standing there with a buzzer, and there's a light going around the screen, and they're saying, no whammies, no whammies, no whammies, stop. And it might be a picture of this little character they called the whammy that would take all your money away, effectively like going bankrupt in Wheel of Fortune or something. But sometimes it would be a cash prize. And the light just kind of, it didn't go around the screen in any kind of pattern. It was just random. It would pop the lights that, the box that would be lit up was random, or at least it appeared to be. So Gary was a super fan of the show, videotaped it every day, and watched it when he got home from work. And he noticed the lights were what are called pseudo-random. In other words, they had about 10 patterns stored in memory, and would randomly pick one of those 10 patterns. But once he saw 2 or 3 lights, he knew where it was going to go next because the patterns were about 10 lights long. So he went and camped out in front of the studio in California, got his life savings, spent his life savings to do this. He got there and went on the show and won like $100,000, which back in the 80s, I don't know, it'd have to be like $1 million today. I'm not sure exactly what the inflation rate is, but it was so funny because the audience were cheering so vigorously for him. You know, like, yeah, go, buddy, when he was like 25, 30,000. Then when he started to get 10, 15, 20 in a row, correct, the audience just went dead silent. And the host was horrified. You know, he says, well, I guess this is our budget for the entire season. You know, the show's going to get canceled over this. So he got the money. They sued him. He won the suit. He ended up keeping the money. Then he got involved in some kind of pyramid scheme and lost it all, got cancer and died. So it's a tragic case, but for that one shining moment, it was a great hero. Gary Larson, that's his name, Gary Larson.
I don't trust game shows, because there's so many cases of people cheating in them.
Agreed.
Like, there's been a couple people on, like the Millionaire Game Show that have like used people in the stands to get like to win money.
Mm-hmm.
I'm like, then why would you have a game show like this?
Well,
I'm so sorry.
That's
It's
okay.
been a while.
that's okay. It's better late than never. Okay, so, let me change to tardy. Okay, so we're talking about probability, Ellie, and the fundamental idea here is successes over total outcomes. So that's the way you measure the likelihood of an event occurring. Now, let's talk about birthdays. It's an interesting thing, and this kind of gives it away, so let me go back to this blank screen here. Just estimate for me, if we had a room of this many people, what is the likelihood that they would share a birthday? Just estimate right off the top of your head. I'll just ask you guys. So if I had a room of 5 people, which is almost what we got here, exactly what we got here if you don't count me, what's the likelihood that one of those people share a birthday with each other? Just estimate, Riley. What do you think?
Not likely.
Not likely. What do you think, like 5%, less? Let's just say 2%. What about a room with 10 people, Colby? What do you think is the likelihood somebody would share a birthday?
5%.
Okay. What about a room of 20, Macy?
7%.
Okay, that's a good guess. We're consistent here. We're just having a little thought experiment. Allie, what do you think about a room of 30 people?
9%.
Okay. And then finally, a room of 50 people, Gracie. What do you think?
12%.
That's good. Consistent. You didn't have to be consistent. You know, there is a way to figure this. So we're going to calculate it and see how good your estimates were. How many people in a room guarantees somebody sharing a birthday if we ignore leap year? We're going to ignore leap year.
366.
Well, 365. If we ignore leap year, then, well, you're right, actually, because if,
sharing.
yeah, so there would be one more than the number of days, so 366, yeah. So that guarantees it. It has to be the case if you got that many people. But anything less will be a probability between 0 and 1. And the way you figure this is kind of interesting. And like a lot of arguments in probability, it deals with finding the likelihood of an event not occurring. Oh, there we go. So the probability of sharing a birthday, that's the successes over the total outcomes, but it's going to be equal to 1 minus the probability that nobody shares a birthday. Do you see what I mean? Like if I flip a coin and I say it's not heads, what's it got to be? So 1 minus the not birthday is equal to the probability of the birthday. Because 1 is these two added together. Now, ways to choose pairs. So I've got pairs of people in a group is n combinations of 2, where n is the number of people in the room. So that's a way I can choose pairs. And the probability that people don't share a birthday is going to be 364 out of 365. We're ignoring leap year because a lot of the mechanisms of probability use factorials, and factorials don't work with decimals. So if I try to go 364 point or 365.25, it would break the formula. So we'll ignore leap year to make our life a little easier. So the probability that people don't share a birthday 364 over 365. And so that probability to the power of the number of pairs in a group is the chance no one shares a birthday, okay? And with anyone else. And so 1 minus that amount is the probability of at least one birthday being shared. So if we plug it into this formula, and remember, this is 364 over 365. Let's use our calculator to find the exact values for those things we guessed at a moment ago. So 364 divided by 365 to the power of, that's where it gets funky. The first one I said was 5. That's how you put 5, choose 2 in your calculator, use that NCR function. So that one is about 97% that nobody shares a birthday. So 1 minus that amount is about 0.02 or just about 3%. So gosh, you guys were close. Great guess on that. Let's try it with 10. So 1 minus, excuse me, 364 over 365 to the I need to insert my number before that. I believe that's right. So that's about 11.6%, so much higher than we thought. This is a much more fun problem when normally my pre-calculus classes are big, like 30 plus kids in some cases. And it's really fun when at the end I start asking kids, and usually I find a pair when it's 30 that share a birthday. Of course, we're a small enough group here for it to set a line. All right, so let's do 20 people in a room. You can hit second enter to bring up what you just put in again. So that's 40.6%. It's wildly deviating from our guesses now. Don't you agree? And we'll go with 30. So again, this is the size of a typical pre-cal class in a normal year. About 69.6% or 69.7%. See how far off we are now? It's amazing, isn't it? So this is what I usually get, and I usually find somebody. Sometimes I do, sometimes I don't, but more than 50% of the time when I have a class that size, I will find a pair that share a birthday. And then the last one we said was 50. %, 96.5%. Bet you would not have guessed that. So in a room of 50 people, it becomes almost certain. Where again does it achieve absolute certainty, as Colby and I discussed? The number of people that makes it absolutely certain. Well, it was 366, remember. So there's a long way between these two, but you see how it approaches almost absolute certainty with much fewer than that in a room. So if I had 100 people, it'd be, almost absolutely certain. It's a fun little problem. And normally I end it by, doing a little like who's born in January, who's born in, but we're too small of a group here for it to be very likely. We're in this. So not a lot of point in that empirical experiment. But you see how greatly it deviated from our expectation, at least after the first one. The birthday paradox. So here's an interesting problem. So a probabilistic problem. So this dude, Abraham Wald, was a scientist in the Second World War, and he was reviewing the damage that planes had when they returned from sorties In other words, missions over Germany in World War II. Now, the Germans had a lot of anti-aircraft weaponry, right? So they were constantly firing at our planes, and sometimes they would take them down, sometimes our planes would make it. I think, in fact, the bomber runs had something like if I'm not mistaken, they were supposed to fly 20 missions or something like that. There was a movie, Memphis Belle, that was about this that I liked a lot. But I think they had to do 20 missions before the crew was retired effectively, and somebody else took their place. And only like 10% or so survived that 20 missions. So a lot of them were getting shot down. So he got these planes back, and they had bullet holes in the fuselage and the wings and other places. And he did something that was just so smart, and it really saved a lot of lives. He decided to reinforce the planes where he did not find bullet holes. Why? So these planes coming back, sees bullet holes in certain spots. He reinforced the other spots. Why?
So they were focused in the important part.
Well, if you're returning with damage to a certain section of the plane, that's clearly a part of the plane that can still fly when it's damaged. The other parts are causing them, because it's, statistically the same probability that they'll get hit anywhere, right? Because the way a flat gun works is it just throws shrapnel everywhere, and it damages the plane uniformly. So where they're returning with damage are non-critical areas. The other areas where we're not seeing damage are critical areas, and the planes that are getting hit there are going down. So this guy did something so smart, he said, reinforce the areas where the bullets are not showing up. I think that's genius. That always struck me as a really interesting thing. And a good application of probability. Here's an interesting probabilistic argument. It's called the Drake equation. You guys heard of this? That's the probability that life exists on other planets. And a lot of it is all of it effectively speculative to one degree or another. Less so now than when it was created in the 1960s. In the 1960s, this was wildly speculative, but nowadays, a little less so. So, the Drake equation has N as the number of civilizations in the Milky Way galaxy whose electromagnetic emissions are detectable. And there's where you run into a little bit of a problem. Because I don't know if you guys have heard of something called the Fermi Paradox. So Enrico Fermi was a great scientist, and he basically asked the question, where the heck is everybody? The universe is huge. And there's plenty of room for other intelligent civilizations to exist. We would expect them to emit electromagnetic waves like our civilization does, TV broadcasts, radio broadcasts, et cetera, et cetera. If anybody were listening for us, they would see us. And yet we don't see other radio broadcasts in our universe. So where the heck are they? That's the Fermi Paradox. And there's a lot of solutions to it. One that makes a lot of sense to me is there's some technological advancement that supersedes electromagnetic communication. It's inevitable. So there's only a narrow window where civilizations would use electromagnets. But there's a lot of interesting other ones. Like, for example, people think maybe civilizations tend to go into a matrix. They create a perfect virtual life for themselves and divest from reality. There are some other weird ones. The great filter, the notion that only predatory species are intelligent enough to get to this tier of technology, and then inevitably they kill each other. Just can't help it. It's in our nature to kill.
Isn't there also a theory that outside of our solar system there's like a wall of energy that's blocking?
I've heard a little bit about that, Colby, but to be honest, I'm not super familiar with that theory. There is the Oort cloud, which is the influence of our sun. It's possible, I suppose, but I don't know that there's a lot of empirical evidence to back up that one. But anyway, so this guy thought about how many civilizations might exist in our Milky Way galaxy. Well, first of all, you have R, and do you remember, well, not a lot of people watch the Chapter 0 video, but in the Chapter 0 video, I talked about making Subway sandwiches in the fundamental choice theorem, which is that if you have event A that can happen M ways and event B that can happen N ways, then together they can happen M times N ways. In other words, if you multiply probabilities together, that's the likelihood of those events occurring together. So that's what we're using here. And R would be the rate of formation of stars suitable for the development of intelligent life. Really speculative. We don't know that certain stars exclusively produce intelligent life. We have a sample size of 1, which is our star. And it produced intelligent life, us. So we really don't know about the other systems. They may or may not. There is a lot of interesting science going on with this, because they'll analyze the atmospheres of exoplanets looking for phosphenes, like what they found in the atmosphere of Venus, that make them fairly certain that bacteriological life exists in the clouds of Venus, which is really interesting because it's where Carl Sagan said we should look. You remember the Cosmos, the original Cosmos, not the Neil deGrasse Tyson one, the original one from the 80s. The host was Carl Sagan, a great geneticist and scientist, and he said you should look in the clouds of Jupiter and Venus. And sure enough, when we looked there, we found evidence of life. Pretty interesting. So what kind of stars create intelligent life? It's hard to say. Our star is a medium-sized star, and it's going to live another couple billion years or so before it becomes a red giant, swallows the Earth, and the solar system effectively will be uninhabitable. But there are other types of stars. There are red dwarfs, which burn quite a bit cooler, they're quite a bit smaller. The Goldilocks zone, in other words, where water is liquid, is pretty small, but they live for trillions of years. In other words, thousands of times what our star's life is. So do you see how if a planet were in the Goldilocks zone around a red dwarf, life would have a lot more time to evolve into an intelligent phase, and infinite more time, effectively. So who knows? It's a largely speculative argument. F sub p, the fractions of those stars with planetary systems. This was not well known in the 60s at all. It was thought that planetary systems were rare. However, the Kepler telescope and other methods we've discovered for finding exoplanets, planets around other stars, has shown that basically every star has a planetary system, almost all of them. And it works, the wobble effect works kind of like this. You guys got younger siblings? You ever take them and swing them around like this? Super fun, makes them scream. But you see how if you're doing that, you wobble back and forth a little bit because of their weight? Well, planets and stars dance like that with each other. And the star ever so slightly wobbles back and forth if it's got a planet. So we can look at it real super close with things like the Kepler telescope and tell. And if we're really lucky, then the plane of the planet is the same as our viewpoint to that star, and the planet will pass in front of it, and it'll dim just a bit every time that planet passes between us. And if that's the case, not only can we know the planet exists, we can know its chemical makeup, because chemicals block certain wavelengths of light. So if we analyze the light from the star before, during, and after the planetary pass-through, we can see what the primary chemical makeup of that planet is, its atmosphere, and so on. Really interesting science being done there. So this is close to 100%. N sub E, the number of planets per solar system with an environment suitable for life. Well, we're 1 for 9, at least as far as we know. If you count Venus and that thing too. But could be much higher. And who knows, there could be bacteria in the ice on Mars. So suitable for life is one thing. Suitable for intelligent life is quite another. But an interesting question. F sub L is the fraction of planets on which that life actually appears. So is life inevitable? If it can be, must it be? I don't know. F sub I, the fraction of life-bearing planets on which intelligent life appears. So that's the real conundrum there. Are we alone in the universe, as indicated by Fermi's Paradox? Or, who knows? That's a lot of range. And we really have no idea. And then the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. And L, this is the one I was talking about where they replace electromagnetic radiation with some other technology, or withdraw from the universe and invest themselves in a virtual matrix world. The length of time such civilizations release detectable signals. So a really interesting and fairly complete, exhaustive analysis, Drake's equation. So this is the details for it. Pretty interesting probabilistic problem, purely speculative. In other words, they're just guessing. There's not a lot of empirical science to back this up. But, an interesting thing to think about nonetheless. All right, questions about probability. Okay, so your task, not a homework assignment from the book. I'm going to give you a Google quiz over what you just heard. It should take you about 10 minutes. Go ahead and do that for me when I open it up here. And for the guys at home, it'll be available when you see this. Oh.